Welcome back, everybody. Well, this is William M. Briggs, and continuing the class of uncertainty and probability theory, the logic of science. As you might be able to tell, there have been some changes, foremost of which is this lovely new video setup I have. Brand new camera that records in a much higher resolution. Light source, so you can see what it is that it's going on the board. I have this lovely new wireless microphone and other things that all to handle how to process the video and so forth. These were very generously donated by an anonymous source who thinks these classes are important, and I am extraordinarily grateful to them. They were all set up by a man named Matthew Bushy, who is out of Milwaukee, who runs a professional video shooting and editing and photography and all this kind of a thing. So if you're looking for somebody who knows more about this than you'll ever need to know, and you need these kind of services, please do look him up. He taught me how to use this equipment, and we're going to see if the lessons stick. The first lesson did not stick. I had this new camera on, and it had face enabled. And I'm up here waving my arms around like a monkey deprived of his banana, and jarring, back and forth so quickly. The thing kept up with me, but when you're trying to watch the video, it looked like one of those cop body cam kind of a things, and someone being arrested. So I had to turn this off, and I'm reshooting the video. All right, so what we're going to do is do a check. We're going to do a logic. We started, we're going to go over this again in a second. We started with wondering, what can we say about uncertainty at all? And we said, all right, we're going to start with logic and see where that leads us. That's what we're going to complete with today. That's how we started in Jane's 6 or 7 classes ago. Well, the 7th class. And I'm starting to get some questions. I'm getting questions all along, but I'm starting to get questions from people who have had training in these subjects before. If you've had training in any kind of statistics class, or a physics class, or in probability at all, of any kind of probability training, in the classical way where you might have called yourself a frequentist, a Bayesian, an information theorist, a physicist, any of these kinds of things. And they're trying to fit into buckets what they have learned about probability before and what I'm teaching now. And they're finding that all of it doesn't necessarily fit. And that's the case. It doesn't necessarily fit. If I was going to teach in the old classical ways of thinking about all these things, I'd never need to teach. There's more than enough material that's out there. So I'm getting questions about random variables and about uniqueness of probability and all that. We'll come to all that. We'll come to all that kind of stuff. So all I want you to do now is don't try to do that. It's a very natural thing to do, to try to fit this new information into the categories that you have. We all do that all the time, and most of the time it's a very useful thing to do. But not in this case, not when I think that the old ways of doing things, or the classic ways of doing things, are flawed. So let's review the first 6 courses just to see what we've learned, and all we've learned. The only things that we've taught. So the first one was, what can logic say about uncertainty? I'm not going to talk too much about that. We're going to review that today. That's going to be our review. Class 2, which I always forget the order. We learned that this is a nice thing about this wireless microphone now. I could have my back turned to the camera and you can still hear me. Before, I was dodging over there. Anyway, we learned that necessary truths were greater than local truths. Of course, there is such a thing called truth, and if you disagree with that, you agree with that. And we learned the difference between necessary and local truths. And we learned the essential difference, which we're never going to forget, that our knowledge of things is different than the things themselves. We're never going to forget that. Epistemology and ontology are not the same. We emphasize that over and over and over again. And number 3, some people were questioning, I don't need this philosophy stuff. Well, you have to have a philosophy of probability. You have to have a philosophy of probability. You have to have a philosophy of how you're going to apply this eventual mathematics to things in the real world. You can't just go strictly by your intuition, because Although intuition, as we're going to see, is very powerful, it can mislead you. And we learned that belief was an act, and we had to have faith. Faith was inescapable. You had to have faith at least that your senses are working to take in sensory information. They don't always work, but on the times you think they're working, you have to have faith. And there's no other proof of that. There's no proof beyond that. Just as there's no proof, there's no proof, well, we'll get to that. 4. Well, again, logic is partly subjective and partly objective. It's subjective. We list out these logical equations, and I'm going to list some for you here in just a second. We list out these logical equations. We come up with these premises. We come up with them subjectively, and we come up with a proposition of interest. And we want to know how those premises that we came up with relate to the proposition of interest. All of those choices we make are purely subjective, but the connection between the premises and the proposition of interest is wholly objective, rigorously objective. Absolutely rigorously objective, because logic is only the study of not where we get these premises. It's not the study of where we get those premises. It's the study of connections between premises and propositions of interest. And the old ways of saying is saying conclusions, but they're not conclusions. We form the propositions of interest. All right. We finally learned, well, we didn't finally learn, but we learned that induction, including intuition, was the highest form of knowledge. There's no empirical proof that, for instance, in math, that axioms are true. The axioms in the sense that propositional statements everybody believes is true, but there's no proof that they're true. They do start with knowledge in our senses, in which you extrapolate to universals using forms of induction and intuition. We went through all of that in this class. So that's very important because there's at least 5 kinds of induction. The strongest is these kind of inductions where we form these universal truths, universal necessary truths, all the way down to induction of the kind of probability. Probability is the weakest form of induction. We did all that. And then finally, we learned that probability can be a function, and that certain function was the only function we've proved so far is at Bayes, and it can be a number, but we only did 2 numbers, 0 and 1. 0 turned out to be false, and 1 turned out to be true. This is the only thing we've done. We turned out, yes, probability can indeed be a number. It has a certain functional form. That's what we did last week, or last class. I guess it was last week. That turns out to be Bayes' theorem, from which we can deduce 2 numbers. That's the only thing we've deduced so far, is 0 for falsity and 1 for truth. This is all we've done. This is an immense amount. We're founding all of this knowledge, all of this on our knowledge of certainty and uncertainty, because probability is going to be about uncertainty. We want to make sure we get this part right. This is the stuff that's left out of all of those other classes that you would have had in the first place. They would have just jumped in and they said, here, probability is these numbers, here's these equations, and go to town. I want to stress, in all those cases, the math is not wrong. The math is almost never wrong. It's how we apply the math. That's where we go bad. So we had to start with all these kind of things. So if you've had training before, and you're a physicist, or you had probability training, or you're a statistician and you've seen all this kind of thing, you're going to wonder what you've learned fits into all this scheme. Well, this is how all that stuff is built up. But please don't try to jump ahead yet. Don't think in terms of random variables and all that kind of stuff. We'll come to all that. But it's going to be not the same as you classically learned. Now, all right, let's go through it. Now, remember, in the very first day, I'm seeing how much, I ranted for 10 minutes. I haven't even began the lesson yet. Ranting and raving for 10 minutes. I guess That's par for the course. We had several equations, logical equations. We wanted to know if they could be, how they could be worked in probability, or what we could say about certainty and uncertainty of them. So we started with an equation: if A is true, then B is true. A, B. This is an equation. Here is a subjective premise. I say if A is true, then B is true. I state that. It's something I'm assuming for these two propositions, A and B. And then I'm going to say I say that A is true. And therefore, what can we say about this proposition of interest B? I picked this proposition of interest B down here. What can I say about B with respect to these things? Well, let's remember our probability formulas. Probability of A and B being true given C is the probability of A given true, given B and C are true, times the probability B is true, given C is true. Or it's equally the probability B is true, given A and C are true, times the probability of A given C. That's Bayes' theorem. That's what we learned last week. That's what we deduced from just simply wondering if probability can be a number. And using, I didn't go through it in class, but all the functional equations and so forth, there's dozens of locations you can look that stuff up. All right, so here, what do we want to know? We want to know, and for simplicity's sake, James and I too will follow the, just so I don't have to keep writing if A then B. I'm going to call this proposition up here C. So C is going to equal if A then B. Remember, this is all just notation. It's all just there to help us. The notation is not real. The notation does not exist. This is stuff about our knowledge about the world, not the world itself. So what do we want to know here? Well, we want to know about the probability of B given A and C. Simple enough. The probability of B given A and C, well, that's equal to, just manipulating Bayes' theorem here, the probability of A and B given C divided by the probability of A given C. Right? The probability of A given C is, of course, equal to 1. And the probability of A and B, since A is true, adding something else to it here, adding this B to it, if A is true, then B is true, just by the rules of logic, is 1. Therefore, the probability of B being true given A and C equals 1. Well, there's no surprise to that, but it does fit in probability. Probability is logic. Logic is probability. This is the scheme we learn. All these formulas work. They should work for any propositions that we care to put in there. You know, barring self-contradictory ones, asinine propositions, that kind of a thing. Okay. Okay, yes. Let me keep that up there. I'm going to keep this up there. And then we learn a second logical formula. And then not A. Well, we learned if A is true, then B is true. And then we also subjectively assumed that B is false, not B. All kind of ways to write that. And therefore, we're interested in this proposition, not A. And remember, one other thing we learned over here before, we also learned last week, we learned two forms. We learned Bayes' theorem, and we learned that this is true, given any probability. We learned that A and its complement, A and its negation, however you want to say it, has to equal 1. Either A or not A has to be true. And so we're interested in not A here, which is equivalent to 1 minus the probability of A being true, given any premises. It doesn't have to be C, it can be any premises that we choose. So we could just manipulate this equation up here, and if it works for A and B, it has to work for any propositions. Okay. Well, probability of, let's do this correctly. Yes, okay. A, let me write it all up. I wasn't going to write this step up, but I wanted to, this is just Bayes' theorem again. The probability of A and B naught is the probability of A and B naught times the probability of B naught. It doesn't matter if it's B or B naught I put in here. Any proposition at all is going to work in here. And so we're interested in, obviously, either A, it's easier to work with A, because if we say something about A, we say something about not A. This is just a mathematical trick. Divided by the probability of B naught given C. Well, the probability of B being false given C is 0. I'm sorry, is 1. What am I saying here? Numerator, dummy. The probability of A and B being false at the same time is 0 given C, and the probability of B given C is 1. B not being, of course, 1. And therefore, the probability of A being true is 0. And if this is 0, it must be that the probability of A being false is 1 is true. All right, simple. Without my horse mouth rendering of the thing, you get the idea. Okay. Those are the simple ones. That's the ordinary logic. And now what we're going to do is there were a couple of other equations in there. We'll still keep that. And finally, we enter the realm of probability. So B. Again, if A is true, then B is true. We're going to assume A is true, not B is true, dummy. No, that's right. We're going to assume B is true. And we're going to say A is more plausible. What can we say about this? These are two subjectively chosen premises, and here is my proposition of interest. Now, if I just had the A, just the proposition A, this then becomes a formal fallacy, as taught in every logic class in the world. And the reason you say, well, A doesn't have to be true, there's all kinds of things that could happen and A doesn't have to be true. And so that's why they leave it off. They leave it off right there and demonstrate that A doesn't have to be true. Oh, absolutely 100% correct. But they stop short. We could say more about A. Why? Yeah, okay. We get the idea that A doesn't have to be true, but what else can we say about A? So let's look at this equation. Again, we have that the probability, we want to say something about perhaps A given B and C. Here's A, and here's B, and here's C. Well, just by manipulating these equations up here, that's the probability of A given C. If you don't see this, just here's the probability of A given C. Here, yes, the probability of A given C, and you just maneuver these equations around, as you'll see. Maybe I'll write it all up, it'll be a little bit clearer. We just used Bayes' theorem. Because these two things are equal, we're able to get out the probability of A given B and C is equal to this times this divided by this. And that's all we have right there. This is a C right there. Okay. Now, we already learned that the probability B is true given A is true and C. This has to equal 1. Now, here comes the innovation. Here comes where we learn something interesting. This right here. This turns out to be less than or equal to 1. This is the innovation. Right here, nothing else. This manipulation of Bayes' theorem is real simple. This is simple. We don't know what this is. We're trying to figure out what this is. We say, given C, if A is true, then B is true. What's the probability B is true? We don't know. But it has to be, from the implied premise that B is possible, that the probability has to be less than or equal to 1. And of course, greater than 0. Because it's possible. we have learned that B is contingent. There is the possibility that B exists. We haven't proven any numbers yet, just that we have a mathematical formula. We don't need to prove any numbers. We're going to use this as an inequality right here. This is all we're stating right here. So it becomes the case that the probability of A given C, we don't know what that number is going to be multiplied by 1 and then divided by a number that's less than or equal to 1. And simple math then says that A given B and C is going to be greater or equal to the probability of A given C. So if A is true, then B is true. We know that B is true. A is more plausible. We know that B is true. C is true. A is more plausible when we know B. That's what we set out to prove. It's an inequality, which means probability can sometimes be an inequality. We don't have to have strict numbers. We don't have nearly enough premises in here to give ourselves a strict number. So there's one way that we differ from the classical approaches where they subjectively, just depending on the state of your meal the night before, come up with a probability for this, or they deny that a probability for propositions can exist, as in frequentism. All of that stuff is out the window, which we're going to go in and cover in a lot more detail. I'm just giving you a hint at where we're going. We have deduced from logic alone that the probability that A is more of course, the entire proposition A is more plausible. The probability that A more plausible, given this argument, all the argument that we did, is 1. We have deduced that this is true. We have deduced the probability of A is more. Probability is logic. Logic is probability. There's no getting around it. Okay. All right. I am going to write this up. So now what have we ever learned here? We have learned we're going to have to keep this knowledge right here. B, C greater than or equal to the probability of A given C. Okay. That's something that we have learned that is true. We have deduced it. Like any other mathematical equation that we have learned is true, we can keep it and use it forever. By the way, I nailed up all these boards yesterday here. I got complaints about the insulation and everything. I haven't had it. I just got these boards done yesterday afternoon. There's nothing, it's all rough, extremely rough, all that kind of stuff, and it's only this wall. The rest of the place looks exactly like it did from previous weeks. I will be attacking that in the interim. Okay. What else did we do? Ah, yes. We learned that A is false and B less plausible. If A is true, then B is true. A is not true. Well, there's always imaginations. We can think of ways that B could still be true even if A is not. So therefore, we can't conclude that B is true or false. So it's a formal fallacy. But we could still say something. We could still say something. This is the only innovation. It's just using, this is all we're doing, is just using the rules of logic to go on and develop what we can say given the information that we do have. And we're going to do it in exactly the same way. Okay. So what do I want to say? I want to say something about the probability of B, given that A is false and C. I want to see if my equations can handle this. Well, I'm just going to use these equations up here again, Bayes. Probability of B and C times the probability that A is not true, given B and C are true. The probability of A and C. Again, I can't stress this enough. These are only assumptions. These are assumptions. It doesn't necessarily mean they're true in the real world. Probability works for local truths, and it works for necessary truths. If these are true in the real world, necessary truths, why then we've demonstrated necessary truths. If these are only subjectively chosen and they're not true, or we don't know they're true, and they're not self-contradictory, then we have a local truth. So probability works with local truths, probability works with necessary truths. All right, now, well, we have, how do we solve this? Well, we have this. This is what we learned a minute ago. And from this, we can deduce, make sure you understand that we can deduce from, and I already erased it unfortunately, but the probability a proposition is true given some evidence, plus the probability of its contrary is true given the same evidence must equal 1. So if we say something about the proposition or its contrary, we're saying necessarily something about the opposite. So we also learned that probability that A is false must then be greater than or equal to, this is just simple middle school algebra here, I guess. We have also, because this is true, the probability of A given B and C must be greater than A, greater or equal to A given C. It must be that the probability A is false must be greater than or equal to A is false given B. You can work that out in algebra if you can't already see it. Now, because of this, well, you can immediately see what's going on here. This has to be greater than the probability of A given B and C. This number is bigger than this number. This number is bigger than this number. Therefore, we're multiplying this number here by a number that's going to be less than 1, less than or equal to 1. And therefore, it must be the case that the probability of B given A is false, C, must be less than or equal to the probability of B given C, which is exactly what we set out to prove. The phrase, the proposition B is less plausible, the proposition B is less plausible given the argument we just did is true, and the probability B itself, given A is false, must be less than or equal to the probability that B is true, given the evidence that we have. So again and again and again, we're going to learn that probability is logic, logic is probability. Logicians, it's kind of odd. They didn't know when they were studying all this kind of stuff. It's easy to see those logical equations, but we come up with counterexamples when we do these kind of things. We come up with counterexamples easily enough, but we also come up with pro-examples to say how B could be false in this kind of a thing. What we wanted to get from this is not, and the reason probably people didn't see it is because we can't assign a number to this. We haven't assigned any numbers at all. All we've done was come up with some inequalities. We have this inequality and this inequality. That's it. We haven't come up with this is true, or I mean, this is 0.5 or 0.6 or some other thing like this. And with probability, people are always wanting to jump right to the numbers. That's the way they've been trained. And that's the way probability in the classical school developed in gambling and so forth. We'll get into all this. And so they had numbers at their hand ready to go. We don't have any numbers yet. The only numbers we have are 0 and 1. The rest of it we haven't deduced yet. But we can see that probability can be inequalities. This is all we can know, just inequalities. So next time, which is going to be in 2 weeks, we're not going to have a class on Memorial Day. We're going to start developing other numbers. We're going to show you that probability can be extended to more numbers than just this. The only homework is going to be is to continue reading in Jane's, this material. I took it straight out of Jane's, gave it a little bit more flesh, but read that. Make sure you understand all this. We haven't done very much here except to emphasize and re-emphasize that probability is logic and logic is probability. And that is all I'm going to do today. Thank you very much for listening. Oh, I'm supposed to give you can go to wmbriggs.substack.com or wmbriggs.com. I'm in Twitter jail right now, again for another week. So if somebody wants to see this and post it on Twitter, they can. Otherwise, I'm famed celebrity right there. This will be on YouTube, Rumble, and BitChute, as well as those two sites. Thank you for watching.